Dear students, in today's lecture we will study about the autotransformer. Sometimes it is desirable to change voltage levels by only the small amount. Like if we want to change the voltage from 110 volts to 120 volts or 13.2 kilovolts to 13.8 kV, then it would be easy to use autotransformer in which there would be one winding instead of two windings. As you can see from the two figures, on the left hand side there is a conventional transformer where there are one is the primary winding and the second is the secondary winding. But in the autotransformer we have a single winding in which we take out a connection and we connect it with the low voltage or high voltage according to our needs, to low voltage in here, in the case where we are going for step up transformer, or if we are having step down transformer, then again this would be connected with low voltage, but this would be on output side. So we will discuss this in detail in next few slides. So in this case we can see that VL is the input voltage and VH is the output voltage. This voltage VH is the sum of VL and in the addition of VSE. VSE is basically a series voltage across a series inductor winding. So series winding, and then there is a common winding. In common winding is the winding across which both the primary and secondary voltages appear, because in this winding you can see that this is connected to the primary voltage as well as secondary voltage. So this is called common winding, and this is the series winding, which is in the series to the common winding, and usually it is a small winding, so this is called series winding. And the voltage at output VH is equal to voltage across common winding plus voltage across series winding. So this is the step up transformer on the right hand side and step down transformer on the left hand side. In the step up transformer, the voltage VL is on the input side, and on the output side the voltage has been increased by, there is also two windings. One is the primary, or we can say the common winding, and then there is a series winding, and the output voltage is the addition of both of voltages across the both of the windings. In the step down transformer, auto transformer, we have VH at the input, and then it has been stepped down to VL, and this VL is calculated against the common winding. By Kirchhoff's law, we can easily find that the IH is equal to I of series. Like if this is the IH, then it will be I going through I series. Similarly, in this case, ISC is equal to becoming the IH, and IL is equal to ISE, which is the series current and the common current. So if this is the IL, this is IL, then we can see that this is equal to ISE plus IC. In both the cases, these equations are correct for both the cases discussed over here. Similarly, we can calculate that the VL and VC can also be calculated, that in this case, in both the cases, you can see that the VL is equal to V voltage against the common winding VC, and similarly VH is the addition of voltage across common winding and the voltage across series winding. Similarly, by having the transformation ratio, we can have this relation between the voltages and the number of turns between the common and series windings. So these relationships would be used in next few slides. By taking the same relationship which we have discussed previous slide, we have taken this relationship in this equation as a blue color, the way it shows the relationship between voltage, current, and the number of windings of primary or common winding and then the series winding. So as we know that V against the VH, which is on the output side, is equal to VC plus VSE, voltage across the common winding and voltage across the series winding. Now we put the value of voltage of series winding from the above relationship, which is shown in blue color. So we substitute the value of VSE and we get this equation, and then as we know that VC is equal to VL, so we substitute VL instead of VC. By taking VL as common, we get this relationship. So if we want to make a relationship with the voltage of input and output of VL and VH, then we can find this yellow equation. Now we come to the current relationship. On the previous slide we had the voltage relationship, and now we are going to calculate the current relationship. This is also on the similar lines. First of all, we take the relationship for the transformation ratio, and then we find that IL is equal to IC plus ISC as discussed previously, and after finding the value of IC from this blue equation and substituting it in this equation, we get this equation. But we know that ISE is equal to output current, or IH. So we substitute ISC with IH. By taking IH as common, we get this relationship, and on taking IH on the left hand side, we can get the relationship between the input current and output current, and that is shown over here in the yellow color. And uh, by having a common relationship between this current and voltage, these two relationships can be combined and can be summarized into this one equation. Now we come to the apparent power rating advantage. So the input and output apparent power may be defined as S in and S out. So at the input side we say that this is equal to VI, so it's low V on the input side and current on the input side. Similarly, voltage on the output side and current on the output side. So Now we derive that VL can be VL and VH, VL and IL are substituted from this relationship into the S in equation. After substituting these values, we come to know that this factor in VL and this factor on IL, which deals with the number of turns, can be cancelled with each other. So the output would be VHIH. And so S in is equal to S out, and we can say this that this can be written as SIO, like the apparent power on the input as well as the apparent power at the output. So it can be seen from here that all the power traveling from primary to secondary in the auto transformer goes through the, not all the power goes through the winding, some also power goes from primary to secondary, and some goes from uh, input to output. If there's a conventional transformer and is reconnected as an auto transformer, it can handle much more power than it was originally rated for. The apparent power in the transformer winding is given by SW. Instead of S in or out, we show over here with SW, where W stands for winding. So SW is equal to IC VC IC or VSE ISC, which means that the VCIC, the voltage and current across the common winding, and VSC ISC, voltage and current across the series winding. So in this case, we know that this is equal to VCIC, but we know that VC is equal to VL and IC is equal to IL minus IH. You can also see from this the Kirchhoff's law, and by uh, multiplying the VL, we get over here the VL IL minus VL IH and VL IL minus VL, and then we put the value of IH from the relationship as we discussed earlier, which is the transformation relationship. So we put the value of IH and we get the equation where VL IL can be taken as comma, and uh, and we take the LCM of NSE plus NC, and if we uh, instead of using VLIL, we can also say that it is equal to the apparent power on input side or apparent power on output side. So we write SIO, and then the relationship between the input or output power and the winding power SW can be found or obtained as shown in this yellow color equation. So this is the input output power over the winding power. So in this case, we also know that this equation describes the apparent power rating advantage of the transformer over a conventional transformer. So the SIO is the apparent power entering the primary and leaving the secondary of transformer as discussed earlier. Similarly, the SW is the apparent power actually traveling through the transformer's windings. That's why it is shown with SW. The rest passes from primary to secondary without being coupled through the transformer winding. That's why the smaller the series winding, uh, would be, the greater the advantage would be. So now it is your homework, and it is your uh, exam. You have to do example 2.7 and 2.8, and if you have the similar questions in the exercise, you can also solve that for your practice. Thank you.